Pleasure to introduce Harry Atwater as our next keynote speaker. Harry earned his PhD from MIT in 1987, and he did a postdoc with us at Harvard before starting his independent research career at Caltech, where he's now the Howard Hughes Professor of Applied Physics and Material Science. Harry's the director for the Liquid Sunlight Alliance, a DOE hub, a program for solar fuel. And from 2014 to 2020, he was director of the Joint Center for Artificial Photosynthesis, DOE Energy Innovation Hub. Atwater's scientific effort focuses on nanophotonic light matter interactions and solar energy conversion. His current research in solar energy centers on high efficiency photovoltaics and photoelectrochemical processes for the generation of solar fuels. And his research has resulted in world records for solar photovoltaic conversion and photoelectrochemical water supply. He's a member of the National Academy of Engineers and a fellow of the SPIE, APS, MRS, and the National Academy of Inventors. He's with us very early this morning, Pacific time, to tell us about new directions for fuels from sunlight.
Okay, thank you very much, Mike, and I'm glad to be back in Cambridge, at least virtually here today. First of all, I'll just check to see if you can see my slides and hear me.
Yes.
Okay,
Yes.
very good. All right, yeah. So what I'd like to talk about today is the subject of generation of fuels directly from sunlight. This is a very interdisciplinary field that really brings together the areas of materials physics, device engineering, catalysis, electrochemistry, and membrane science. And it's really a fantastic interdisciplinary arena for scientific and technology collaboration, as illustrated by the sort of unit processes that are described on this schematic diagram of how a solar fuels generator works. And a solar fuels generator, what we are looking to design are artificial mimics of photosynthesis, where the elements harvest light, separate charges, in that way resembling a photovoltaic cell, but in a very different fashion. Instead of driving the charge carriers into external contacts to drive an electrical load, they perform redox reactions on the surfaces of the solar fuels generator, for example, oxidizing water and reducing protons to form molecular hydrogen, or reducing carbon dioxide to form reduced forms of CO2. And what I'd like to do today is to give a broad overview of this field and where it's going and where it's been. And so as a reference point, I'll start with the situation where the world's leaders were gathering in Paris in the fall of 2015. And in the same month when the G20 leaders gathered together and really began to forge a worldwide consensus about climate change, this fellow who started a little software company in Seattle published a white paper called Energy Innovation, Why We Need It and How to Get It. And in it, he plotted or charted the carbon intensity of our economy and in terms of grams of CO2 per kilowatt hour, and the paths that we would need to be on in order to follow a 2 degree, 4 degree, and 6 degree scenario. These are the three colored lines. And the dashed lines represent the carbon intensity of the new energy services that we would add to the economy as the economy grows worldwide. And what you can see is that in order to stay on a 2 degree scenario, the projections are that we would essentially have to, at the moment, be essentially have already decarbonized. So this really illustrates how dramatic the transitions are that are required. And I think this argues not only for the idea that we should be doing decarbonization, but that eventually we will need negative emissions, which Professor Hatton talked about earlier, and that this eventually will grow to be a very significant part of our energy economy. So I think what we're all envisioning is that eventually we will, and what we desire to do is to transform our infrastructure to look something like this, where the basic engine that we have of solar energy, which produces other forms of energy like wind and hydropower, produce either electricity or right now, but an infrastructure for things like ammonia and CO2 and hydrogen that would enable us to realize this vision. And of course, this requires a massive change in infrastructure, but it also requires the means to synthesize at scale these feedstocks that would really power our circular economy. So another thing I think that's very interesting to reflect on is a lesson that at least I learned in my science and technology lifetime, which is that in technology, change is exponential, and that's not true in every field. And you know, we're, as technologists and scientists, I think we're used to this idea, but it's, I think, worth thinking about the fact that if we take the example of photovoltaics, we can say that new energy technologies like IT, like the famous example of Moore's Law, follow exponential experience curves. So for example, when I was, shortly before I arrived at MIT in 1979, the world had, the entire world's aggregate output of photovoltaics was about 1 megawatt. That's risen to 400 gigawatts in 2018. It's around 800 gigawatts now, and probably early next year, sometime or mid next year, the world will actually reach a terawatt of installed photovoltaics in terms of peak electricity generation. And this represents a greater than 500 times cost reduction over the history of the photovoltaics industry since that time I was a graduate student. And you can compare that on this scale and see on the semi-log scale, the change in the price of photovoltaics. And it changed by between 2 and 3 orders of magnitude. That's quite, not quite as impressive as computing. Moore's Law allowed us to run over 7 orders of magnitude. But notably, the price of oil, modulo some year-to-year fluctuations, has remained essentially constant over that entire interval. So I think what that tells us is something very interesting as technologists, that we can look forward to, this cumulative experience curve reduction in cost and increase in performance as we scale technologies. So in sunlight to electricity, of course, photovoltaics arguably is the world's largest optoelectronics industry. As I mentioned, we're about to pass a terawatt of installed photovoltaics. We have more than 100 gigawatts of manufacturing capacity worldwide. Module costs have dropped from the hundreds of dollars into the tens of cents per peak watt as fabricated at the factory door. And modules now cost typically in the range of $50 to $60 a square meter. That's less than the installed, or less than the fabricated cost of a window in your home. So that's, I think, quite an impressive achievement. Of course, photovoltaics has some of the challenges of both daily and seasonal variability. Photovoltaics is predictably intermittent in the daytime. It's somewhat countercyclical with wind generation, but it's not matched perfectly to, if you take those two together, to match to the demand curve. So we need some dispatchability to our energy supply. And that's particularly true if you look particularly at northern latitudes. We have dramatic seasonal solar variability. This is from Sweden, from Gothenburg in Sweden, where the solar radiance varies by a factor of 10 from summer to winter. And we're not going to be able to probably store solar electrons over a entire seasonal period, and so we need other forms of energy storage to do this. So when I think about the path forward, I see two possibilities. One is that on the seconds to minutes to hours to days to weeks timescale, we will see increasing deployment of large-scale photovoltaics together with electricity storage in the form of both lithium-ion and other kinds of solid-state batteries, perhaps also flow batteries, and then also the need to store chemicals, store sunlight basically in the form of chemical fuels. This as one of the densest storage media for storing the energy of sunlight. So we can think then also, once we have paths for transformation of, for particularly carbon dioxide, to generate not only energy storage, but to create chemicals for our basic downstream chemical and industrial economy, using methods of electrochemistry, either direct artificial photosynthesis or indirect processes where we harvest sunlight with photovoltaics or wind, use electrochemical processes to create chemicals and fuels. We can also think to use the energy of sunlight to allow us to bypass the CO2 emissions that are a big part of our current economy in industries like cement and steel, which are among the major single contributors in the industrial sector to CO2 emissions. And this depicts at least one process using electrolysis of limestone to form lime and graphite instead of CO2, using an electrochemical means to produce cement. So we could also think about use of fuels from sunlight to create fertilizer. Of course, we know that the Haber-Bosch process has been transformative for the world's food supply. And the Haber-Bosch process actually consumes something of the order of 2 to 3% of the world's energy output for fertilizer in the agricultural sector. So finding renewable energy sources to drive that process for ammonia, fixing nitrogen and ammonia could be a big contributor to our circular energy economy. And then finally, sunlight directly to fuel. And this is a sort of artist conception of what a solar fuels gigawatt scale plant would look like, generating hydrogen directly by artificial photosynthesis. So what is artificial photosynthesis? This is essentially a process by which inorganic structures, light harvesting materials derived from semiconductor physics, coupled together with electrocatalysts, inorganic and molecular electrocatalysts, is used to mimic the example of nature in which we separate charges to perform water oxidation, generating protons. And in a two-step process, photosynthesis uses two light-driven steps, photosystem 1 and photosystem 2 in chlorophyll. And then those protons are used as reducing agents to produce ATP and NADPH from ADP and NADP in using the Rubisco catalyst in the Calvin cycle. And in artificial photosynthesis, we imagine something that looks like this, like a tandem photovoltaic structure where we take two light harvesting elements. In fact, 2 is about the right prescription for efficient semiconductors. It could be as many as 3. In order to generate the necessary photovoltage required to overcome the thermodynamic really required energy for the transformation, plus the overpotentials that allow us to drive these reactions that overcome the finite essentially parasitics due to the finite turnover frequencies of catalysts for water oxidation, and here shown as hydrogen evolution or water splitting. So that's the basic idea. We absorb light across two photoelectrodes that are in tandem, perform hydrogen evolution at one at a cathode, and then water oxidation at an anode. So the reactions, of course, are the hydrogen evolution and the water oxidation reaction for water splitting. In carbon dioxide reduction, we typically balance, as a source of protons, we use the oxygen evolution reaction. But for carbon dioxide reduction, we, of course, have many pathways. Carbon is one of our, carbon chemistry is among the richest in our periodic table. And there are many possible pathways for reducing carbon dioxide through proton-coupled electron transfer or direct electron transfer to produce formate, methanol, methane, and as well as multi-carbon products. So one thing to note, this concept is not a new one. This is something that dates back almost 50 years to some seminal work of Fukushima and Honda, who first used titanium dioxide and platinum as a photocell to split water on water photolysis in 1972. And this idea was amplified by Melvin Calvin of the Calvin cycle, who envisioned a process by which things that he saw as analogs to micelles and organelles in a biological context, but created as catalytic centers, inorganic catalytic centers driven by artificial light harvesting elements. And the basic scheme here focused on photocatalysis at individual reaction centers. In the case of Fukushima and Honda, it was the hydrogen evolution reaction on the platinum electrode, which balanced the water oxidation on titanium dioxide. And similarly for Melvin Calvin. And over the intervening years, there was tremendous progress. Finally, in the early 2000s, when the Obama administration came into the White House in 2008, then Secretary of Energy Chu launched energy innovation hubs. One of them was the Joint Center for Artificial Photosynthesis that began its work on solar fuels in 2010. And this has recently concluded the work of the DOE hub. So I thought I'd tell you a little bit about the story of the DOE Joint Center for Artificial Photosynthesis Hub, or JCAP. So in 2010, I think it's fair to say that with regard to solar fuels generators, there was only the vaguest of concepts as to how to actually build a solar fuels generator, an artificial photosynthesis device. And high efficiency and high selectivity solar fuels conversion components and generators hadn't been realized. There were not standards for benchmarking of materials and systems, and there were no sort of common best practices on how to do this. And during the course of the 10 years that JCAP ran its course, there was tremendous progress, both within JCAP and in the entire community worldwide. There were efforts, also in single PI labs in the United States and central efforts other places in the world, in Japan and China, Korea, and in Europe. And in JCAP, the combination of intensive hub scale effort on light absorbers, understanding this mechanisms of catalysis for the water oxidation and hydrogen evolution reaction, and development of new catalysts, building prototypes and understanding how they work and how they don't work, culminated within a 5-year time frame in producing a solar fuels generator that reached the JCAP target of greater than 10 times the efficiency of natural photosynthesis. So if you use as a benchmark 1% efficiency as a kind of an average a fleet average for photosynthetic biomass, then 10% solar to fuel generation was the benchmark, and that was met in 2015. And in 2015, JCAP changed course and began work on studying, using its foundation for solar fuels systems to address carbon dioxide reduction. And that is a much more complex set of reactions, as I've described. And it requires thinking about selectivity. We want to generate a single product, not a whole portfolio of products, and that's a big challenge. And over the course of the time between 2015 and 2020, a lot of effort went into understanding and mechanisms for catalytic selectivity, achieving selectivity, integrating these with photocatalysts, and building testbed systems for solar fuels generators for carbon dioxide reduction. So that's a quick survey. And this shows, for example, one of the outputs of this, which are unassisted solar fuels generators for generation of hydrogen by water splitting using earth-abundant catalysts for water oxidation and hydrogen evolution. Both photoanode and photocathode devices were developed, and the fuel products separated using proton and anion exchange conducting membranes. So several years later, and essentially this paradigm development for how a solar fuel generator looks and operates essentially created a clear pathway for progress. And just like any time, in other technologies where one has a roadmap, once you have a roadmap, then people can begin to do design and really tailor designs to achieve the limits of the roadmap. And so this illustrates what is the now current record for integrated photoelectrochemical water splitting of 19.3% that was achieved in 2018. And that was the culmination of a period of rapid development of increase in the efficiency of water splitting devices for photoelectrochemical water splitting, where the device produced in 2018 reached about 85% of the theoretical limiting efficiency for the set of semiconductor band gaps that were used in that device. And just a little look at some of the under the hood of this world record water splitting device. How is this achieved? First, it uses a tandem photoelectrode that's shown here in the red, the orange and yellow, low and wide band gap elements of the photoelectrode. The dark lines here are the quasi-Fermi level splitting diagrams that show the photovoltage produced between the electrochemical potentials for electrons and holes. And that was used to now deliver electrons to a photocathode here, which were the catalyst that was used to facilitate hydrogen evolution was a rhodium catalyst. That rhodium catalyst was produced as an array of nanoparticles. And you might think, okay, well, if you now precipitate nanoparticles of a metal on the front surface, you're going to obscure and shadow some of the incident sunlight, and it's going to be a parasitic loss in the conversion efficiency. But it turns out that at this size scale, the rhodium particles act as little plasmonic absorbers, and their absorption is confined entirely in the ultraviolet part of the spectrum, which is beyond the range where the photoelectrodes produce photovoltage. So within the range of the quantum efficiency of the photoelectrodes, these rhodium catalysts are effectively transparent on the front surface of this device, yet they drive hydrogen evolution at the exchange current densities and turnover frequencies that are necessary to keep up with the solar photocurrent density. So this is a sort of serendipitous occurrence where we have effectively a transparent catalyst. Then the catalyst was produced on a protective barrier of titanium dioxide. This roughened titanium dioxide also acts as an anti-reflection coating, and that anti-reflection coating essentially, together with the rhodium catalyst, produces no change in the optical absorption relative to that of a semiconductor absorber with no rhodium and no titanium dioxide. It's quite remarkable. Furthermore, this front window layer on the tandem photoelectrode smooths out some of the spikes, the energy barrier spikes, like this one right here in the conduction band of aluminum indium phosphide, which is the semiconductor window layer for this tandem photoelectrode. Smoothing out that energy spike by putting on a titanium dioxide coating now effectively lowers the resistance for electron transport to the catalyst to perform hydrogen evolution. So using different compositions of titanium dioxide is possible to tailor this and to achieve here using this particular formulation of precursor for making titanium dioxide to reach that record efficiency. So the story is one of efficiency. However, a key challenge for this entire field, for this device and this field, is that these electrodes, which are derived from the photovoltaics arena, where we can produce high efficiency photovoltaic devices, are not electrochemically stable over the pH range of pH that are experienced in operation in water splitting. So a key challenge for the future of this entire field is to develop photoelectrodes. And in fact, there are now emerging roadmaps by use of Courbet diagrams in a materials discovery approach to identifying electrochemically stable photoelectrode materials. So that is a key challenge for the field. We know, of course, today, when you buy a photovoltaic panel, it's warranted for operation for 25 years. And so this is really the kind of timescale we have to get to with solar fuels generators. So, and this just to tell a little bit about the story here, that titanium dioxide coating, protective coating on the front surface can be effectively reduced if the pH drops down here into the 1 to 0 range. If we operate near neutral pH, where it is possible to actually operate, then the titanium dioxide is more stable. But even locally right at the cathode surface, the pH does drop. So this reliability and durability issue is very much a concern. So this illustrates essentially a recap of all of the records for solar hydrogen efficiency generation, starting from the time of Fukushima and Honda, and then culminating finally in this final record that was generated in 2018. And you can see the upward arc of progress that began to embrace tandem photoelectrodes and different materials, and was really accelerated, as you can see here, starting in 2010, when there was intensive effort in this community. So another key feature that the field of solar fuels needs to address is, of course, our burgeoning need to close the carbon dioxide emission cycle. And many people in our community are very interested in developing this circular economy for carbon, capturing carbon dioxide from the oceans and the atmosphere, from fixed sources of emission in our industrial economy, capturing and compressing it. And then, of course, we need to sequester it or turn it back to a useful fuel, chemical, or material by one of these transformation processes: photochemical, electrochemical, biochemical, and thermochemical. We could use those products and use them as fuels, in which case that cycle begins again, or we could choose to sequester them either in our built economy or literally underground in some geologically stable sequestration site. And of course, we're facing the fact that current emissions at about 10 gigatons of carbon per year are overwhelmingly dominated by fuel combustion at the moment. So we really have to reduce our addiction and fixation to fossil fuels, particularly in the transportation sector. But once we know what our current emissions are, that gives us now some pathways to think about where we could go back to. So obviously, liquid fuels represent one of the biggest reservoirs that we could create. We could create reservoirs, for example, for carbon in substitutes for concrete and steel, for polymers, for specialty and commodity chemicals in the chemical industry, and then also as opportunities for sequestration. So carbon dioxide reduction is desirable, but the question is, how feasible is it? And one of the big challenges is achieving catalytic selectivity, producing the product that you want without producing other products that you didn't intend to make. And this is illustrated probably best by our most competent inorganic electrocatalyst for carbon dioxide reduction, which is elemental copper. So copper produces an entire zoology of reduced products of carbon dioxide upon electrocatalytic carbon dioxide reduction, either in a liquid electrolyte or in a gas diffusion electrode. And this can be understood, that's shown here in the data on the left, illustrating the partial current densities for here methane and methanol, but also created are things like formate, or carboxyl, and then also an array of minor products, multi-carbon products, such as ethylene and ethanol, and then acetate, and among others. And one of the key challenges is that as we bring carbon dioxide to an electrocatalyst surface, and it's activated by physically and chemically bending the carbon dioxide molecule, that process is essentially dictated by carbon interacting with the electrocatalyst. And the local environment in that catalytic process, of course, those who are familiar with catalysis know that it's an extremely local process. And so what we find is that there is a scaling, for example, of the binding and therefore the catalytic activity for example, carbon dioxide and other reduced forms of carbon, say carbon monoxide or CHO or CH2O, COH, formic acid. And that scaling makes it very difficult on an inorganic electrocatalyst surface to achieve selectivity. You can either use strong binding metals like nickel or rhodium, or you could use weak binding metals like silver and gold. So that adjusts the rate of catalysis and the resonance on the surface, but it doesn't allow for great gains in selectivity of one product versus another. So we also have very complex reaction pathways. I won't go into this in detail, but this reaction diagram that's postulated for carbon dioxide reduction to form C1 products, single monocarbon products, and C2 products, dicarbon products, has multiple pathways by which a initially adsorbed, say, carbon monoxide on the surface is hydrogenated and, for example, dimerized, either forming CC dimers or which could be hydrogenated. And so there are these multiple pathways give rise to lots of opportunities on the landscape to produce different products at different rates. So just to summarize where we are at the moment, it was a lot of work that culminated from a huge amount of effort by catalysis researchers and solar fuels researchers and those working on photodynamics of electrodes. Over the last few years, we've seen rapid advances in the contributions of first principles calculations and theory to predict thermodynamic landscapes for carbon dioxide reduction that reveal how the thermodynamic and kinetic processes occur. We now have ideas of the catalytic energy barriers and solvation effects that affect selectivity. Are our models perfect? No, they are not. They're very much a work in progress, but they're starting to really produce useful guidance for the entire field. Likewise, we've also, as I've shown by one illustration, designed prototypes using multiphysics and multi-scale modeling. That's led to high efficiency prototypes for water splitting. And I didn't talk about this explicitly, but similar results have been used, similar device prototypes have achieved over 19% photoelectrochemical CO2 reduction from carbon dioxide to carbon monoxide, one of the simplest reduced products of carbon dioxide. And there have been advances in achieving multi-carbon products by electrochemical reduction, particularly in mixed gas and liquid electrolytes, things like gas diffusion electrodes. But that's really been a story of dark electrocatalysis so far, and being able to selectively convert CO2 to liquid fuels by direct solar-driven processes has really not advanced quite as far. And as I indicated, durability and lifetime of components is really a key issue. And there are many challenges outstanding, mechanistic, controlling light and the flux to the catalytic center, measurement and control of pH, and creation of multi-carbon products. So as we think about this, we could face essentially a choice between two different sort of paradigms for going forward. One is to design, by dint of very inspired catalytic architecture, a single catalytic center that performs multiple coupled proton electron transfer steps that produce first a single intermediate and then use that intermediate to then produce a final product that goes beyond, for example, monocarbon products. Or another alternative we could take would be to break up the catalytic process into multiple steps, a sequential or tandem cascade kind of catalytic process. The unit efficiency of each step has to be very high in order for this to be practical, but it offers a route towards creation of complex multi-carbon products. And so that is effectively a paradigm shift that's underway at the moment. And one example there are two newly established research centers, one at Chase at the University of North Carolina and its partners, and the Liquid Sunlight Alliance at Caltech and its partners, which include Berkeley Lab, SLAC, NREL, UC Irvine, San Diego, and Oregon, which are seeking to push forward using this coupled microenvironment paradigm. So essentially, coupled microenvironments which harvest sunlight, dilute sources of carbon dioxide from air and seawater, and produce complex multi-carbon products like liquid fuels. And this requires, there's a huge amount of data and many chemical pathways, and so the design space is not deterministic or straightforward. And so the design approach that the team is using is what's called a co-design approach, where we start out with objectives and then work backwards in the design to achieve the component elements that are required for the system. So there are three elements to this project. One is to understand and integrate coupled microenvironments, tailoring molecules and materials around the active site, tailoring the availability of CO2, availability of protons and hydroxyl, essentially the availability of the active catalytic site, and then finally separation and transport for the products coming away from this catalytic site. Second is to really focus on the photodynamics from charge generation and its relaxation and transport and interfacial charge transfer to the catalytic center, which is a story of time dynamics and over a wide range of space and time scales. And third is to really understand the underlying processes that affect the combination of durability and performance. So far, the solar fuels community is focused on performance and has made impressive strides, as I've illustrated with a couple of examples. But coupling those together with durability, so we have effectively what's called a volcano diagram, a height of activity in terms of catalytic performance and efficiency for harvesting sunlight, but also durability as well, essentially a multidimensional design space where reaction rate is now considered as a function of these two independent variables. So I'll just illustrate a couple of examples. I think time is a little short. I've got about 5 or 10 minutes. Let me ask, first of all, Mike, tell me how much time I have left so I don't overstay my welcome here.
I think you have 10 minutes left.
Okay. All right. I'll talk for about 5, and then we'll entertain any questions then. So this illustrates one of the opportunities for cascade catalysis, and this shows the essentially the comparison of carbon dioxide reduction and carbon monoxide reduction on an electrocatalyst surface or copper electrocatalyst surface, and that showing the partial current densities that arise from carbon dioxide reduction here in the circles, and filled circles and the carbon monoxide in the open symbols. And what you can see here is that the selectivity, essentially the ordering of partial current densities, is approximately the same for these two reactants on the surface of a copper electrocatalyst. What's different, of course, is their energy, the working electrode energy that's required to drive that transformation. So what's interesting to think about is that by adjusting the pH in the electrolyte, effectively we can do two things. We can lower the voltage and therefore the energy required for the transformation, in this case for CO reduction, and the overall process for both oxygen evolution and CO reduction can be made smaller at higher pH. Now, if we'd use carbon dioxide will complex and form potassium bicarbonate or metal bicarbonates in solution. But carbon monoxide is soluble in the electrolyte, even at high pH. And we also have an additional benefit, and that has to do, shown on this plot at the right, but at very high pH, we can achieve catalytic carbon dioxide reduction at extremely low applied potentials. This is a win-win situation where the applied voltage and therefore the energy required for the transformation is reduced. Plus, we achieve selectivity at high pH with respect to carbon dioxide over hydrogen evolution. So if we're trying to drive carbon dioxide reduction rather than hydrogen evolution, we can enjoy this benefit by going to large pH values. So what this illustrates is that we could break up the catalytic process of carbon dioxide reduction into two steps. First, carbon dioxide reduction to carbon monoxide reduction at near neutral pH, and then a second step at high pH where carbon monoxide is now reduced to multi-carbon products. Similarly, we can also tailor by controlling the availability and the functional behavior of the catalyst sites on inorganic catalysts like copper using additives, molecular additives, organometallic complexes, things like metal organic and covalent frameworks, and metal-free polymer films. So this is one example from the work from JCAP and Lisa, from Agapi and Peters, that showed that dimerized pyridine additives added to an electrolyte condense and form a film. These generate highly selective carbon dioxide reduction to C2 products and suppress hydrogen evolution. I'm going to skip ahead through this set of slides, but I'll just note that this, in a collaboration with Ted Sargent's group in Toronto, this yielded now highly selective reduction of using these molecular additives of CO2 to ethylene with greater than 70% Faradaic efficiency at high current densities with stability over hundreds of hours with a full cell energy efficiency of about 20%. So these are, work is advancing rapidly in this area. Another key area is in controlling the local pH, and a very interesting finding recently came from that lab of Shannon Betcher, who looked at water dissociation catalyzed by the presence of metal and metal oxide catalysts, and found that the minimum energies required for catalyzing these reactions are as low as 20 millivolts. And this gives us now an opportunity to use water dissociation as a tool for locally tailoring the proton on hydroxyl environment, and then using things like bipolar membranes to separate the two and create local microenvironments that have either high or low pH. So I'm going to skip ahead through some of this work here, and in the interest of time, and just note that durability is a key objective, and achieving enhanced durability, and that really requires us to understand processes on both catalysts and photoelectrodes, where we understand the atomic diffusion and atomic transport processes and how these both affect the change in the catalyst activity and selectivity, but then also just the gross reliability or durability and performance of the device at all. So in other words, inhibiting overall corrosion. And great progress has been possible through the use of methods of accelerated discovery using high throughput experimentation, combinatorial synthesis techniques like this, in which inkjet printing on libraries of compound materials. Here, this is a photoanode material, iron bismuth, vanadium oxide photoanodes, quaternary photoanodes, which are then tested using a very rapid scanning droplet photoelectrochemical cell that allows the several orders of magnitude increase in the data collection efficiency for electrochemical and photoelectrochemical measurements. That combined with first principles theory, both using sort of medium level DFT, PBE, and also hybrid functional methods have been used to determine band gaps and band edges and assess stability in water. And together, these have yielded this might be of some interest to the audience here, the largest available database for electrochemistry, at least to our knowledge, with several million compound records of the photoelectrochemical performance and electrochemical performance for alloys containing these materials. This is an openly available database, the so-called MEAD database that's available at this URL. It's searchable by all of the instruments. That multiple techniques were used to characterize these materials, and it's searchable in terms of the types of measurements made, the way in which the materials were synthesized, all the way back to the chemical constituents out of the Aldrich catalog. So there's a hierarchical database that allows you to trace the history of each of these materials and use the data. So this may be of interest to other electrochemical oriented work. So this has yielded, for example, as an example of a hit in the photoanode discovery effort, that iron tungstate exhibits an oxide photoanode that exhibits an unusually large photovoltage, and we're trying intensively now to understand why this is so and how it works. It also has yielded, for example, a big challenge, which is to identify acid-stable oxygen evolution catalysts of broad interest for electrochemistry. And it turns out that manganese antimony compounds represent a very interesting direction to look that allow high activity and stability under low pH conditions. So what I've tried to do here today is to essentially give you a tour of some of the methods and approaches used to create new materials and systems for solar fuels, which has allowed us to produce records for water splitting and carbon dioxide reduction by integrated photoelectrochemical methods. Durability and scalability remain outstanding challenges. And there's I think also an exciting direction for multi-carbon product synthesis, and it really demands a new paradigm, breaking up the catalytic process into a tandem or sequential or cascade process to produce multi-carbon products for dicarbon products and beyond. And a key aspect of this is control of the local pH. So yeah, thanks for everyone's attention.
Thank you very much, Harry. There's a few questions in the chat. Given the time, I'm going to try to synthesize some of those thoughts into one, which is you have enormous engineering challenges here in photoelectrochemical conversion to fuels. All the nano engineering and the band gap engineering, the compound semiconductors to do the manage the photons, and then managing the molecules and all the chemistry. And you're competing with just plain old photovoltaic electricity and plain old electrochemistry, where that photovoltaic electricity can be the cheapest electricity on the planet. And, it is very well established and rugged. Under what conditions do you see that it can be a technical and an economic for photoelectrochemistry over PV plus
Okay, yes. Yeah, no, this is always the first question I get. So thank you for asking it. Yeah, let me just make a couple of observations. One of the things that I think that's true is that what the world of photovoltaics has taught us is not how to make cheap electricity. That's certainly one thing, but how to create integrated, panelized, gigawatt scalable energy transformers for sunlight in 1 meter square units. And that same process, essentially many of the same fabrication processes and methods are equally applicable to PEC as they are to photovoltaics. But that, that's only one element. That's a necessary but not sufficient condition for, say, making an argument for PEC versus PV plus electrocatalysis. The other would be that there are synergistic opportunities to combine, for example, temperature variations, where the Arrhenius rate law dictates that chemical reactions speed up as the temperature increases, even though the photovoltage of a semiconductor typically decreases as temperature rises. So you can actually, and it turns out that those two roughly offset one another. And so one can imagine that as a possible efficiency benefit. Furthermore, I think we can look at the example, if we sort of allow ourselves to think a little more expansively, the example of nature, which in the Calvin cycle, plants respirate through an entire diurnal cycle where they take in sunlight and water and carbon dioxide, and then respirate oxygen, and then create sugars and starches in their leaves. And that occurs on an entire cycle. And one can imagine using the combination of capture together with transformations, as we mentioned, as to close the carbon cycle requires the two of these processes, that would be something that would be naturally something we could integrate into photoelectrochemical device structures, taking advantage of the large area format. So it's a sort of range of answers to that question. Ultimately, things will be dictated in the marketplace by the cost of doing them. And I think it's foreseeable that PV plus electrocatalysis is something we can do today, but there are some techno-economic models that indicate the feasibility and the desirability, haven't yet been built, of course, at these scales for large-scale systems for PEC.
All right, thanks very much. There's a couple other questions in the chat, Harry, but we need to move on. If you wouldn't mind looking at the chat, and if it's easy to type some answers, that would be a useful thing. But it's